Have you ever stopped to think about where the digital keys to your most sensitive data actually live? I mean, think about the physical keys you carry around every day.
Right, like your house key.
Yeah, exactly. You can literally feel the weight of your house key in your pocket. You know exactly which lock it opens, you know exactly who has a spare copy, and you usually know exactly where you left it.
Usually being the operative word there.
Right. But a digital key, we're
Yeah,
talking about an API credential that grants access to maybe millions of user records or even a corporate bank account. It is really just a string of characters, like a ghost in the machine.
a very powerful ghost.
Totally. So where does that ghost actually live? And, how do we keep it from falling into the wrong hands without bringing our entire application to a grinding halt?
That is the big question.
It is. Welcome to today's deep dive. If you are building software in the cloud or even just managing teams who do, this one is entirely for you.
Yeah.
Our mission today is to figure out how to securely store and retrieve sensitive API keys in a serverless architecture.
Specifically looking at AWS.
Right, Amazon Web Services.
Right.
And doing all of that without sacrificing an ounce of application speed?
Which is arguably the ultimate balancing act in modern software architecture. I mean, security and speed are just constantly pouring in opposite directions.
Oh, absolutely.
Lock down your system too tightly with heavy encryption and constant verifications, and your application becomes unbearably slow for the end user. But prioritize raw speed above everything else, and you essentially leave the front door wide open for attackers.
And navigating that tension is what makes today's source material so compelling. We are looking at a fictionalized tech blog post called The Secret Life of AWS The Vault.
Written by Aaron Rose over at tech-reader.blog.
Yes, and I absolutely love the framing here. Rose takes these incredibly dense, complex architectural lessons and wraps them up in this highly engaging narrative.
He really sets the scene well.
He does. He sets it in this grand Victorian library in London. We follow two developers. There's Margaret, who is this seasoned, razor-sharp senior engineer.
And Timothy, her junior colleague.
Right. And in this environment, they treat code quality as an unspoken objective. Craftsmanship is quite literally all that matters. It grounds the technical stakes in a very human reality.
The human element is crucial because, well, before we can dive into the mechanics of how to properly lock down a cloud environment, we really need to examine the psychological traps developers fall into.
Oh, definitely.
There is this pervasive trap of good enough security in our industry, and it is incredibly easy to justify.
Which brings us straight to the inciting incident of Rose's story. So Timothy is deep in the weeds. He is reviewing his payment Lambda function.
Right, and for listeners who don't spend their days in the AWS ecosystem, Lambda is essentially a compute service.
It lets you run code without having to provision or manage your own servers.
Exactly. You just upload your code, and AWS runs it whenever a specific event triggers it.
Now, a little context from the source material. In a previous lesson, which was episode 67, Their Universe, Timothy used an observability tool called AWS X-Ray and discovered that their external payment gateway was causing massive latency spikes.
So his primary focus right now is entirely on looking at his integration logic.
Yeah, he's just trying to optimize a simple connection timeout.
His mindset is purely focused on performance and reliability. He just wants the checkout process to be smooth. Security isn't even on his radar in that specific moment.
Then Margaret walks into the studio. She glances over his shoulder at his monitor, and she zeroes in on the AWS console tab he has open in the background. And she catches a massive, glaring flaw.
A huge one.
The production API key for their payment gateway, the actual key used to process real money, is sitting right there in plain text in the Lambda environment variables.
And Timothy defends the setup immediately. His defense is actually a textbook example of how developers justify taking shortcuts.
What does he say?
Well, he points out two things. First, he notes that keeping the key in an environment variable keeps it out of the source code repository.
Which is true.
It is. And second, he argues that environment variables are encrypted at rest by AWS anyway. He genuinely believes he is following modern security best practices.
Okay, let's unpack this. Because on the surface, Timothy's logic sounds completely reasonable to a lot of people, especially if you follow older software methodologies.
It sounds very standard.
Right. Keeping the key out of the source code, out of GitHub or whatever repository you use, is obviously step one of security. If we think about building a physical house, putting a key in the source code is like printing the master key right there on the architectural blueprints for any contractor to copy.
Which you obviously wouldn't do.
Exactly. Timothy successfully avoided doing that. But keeping a highly sensitive API key in an environment variable, that is basically like hiding your house key under the welcome mat.
That's a great way to put it.
Sure, it is technically not sitting in the lock and you didn't leave it in the blueprints, but anyone who walks up to your front porch can easily flip over the mat and find it.
And the front porch in this analogy is the AWS console. Margaret corrects him on the spot. She explains that environment variables have a very specific architectural purpose, and that purpose is definitely not for storing sensitive credentials.
So what are they for?
They are designed strictly for non-sensitive configuration data. We are talking about things like database table names, basic routing URLs, logging levels.
Like whether you want verbose debug logs or just error logs.
Exactly. Or, ironically, the very timeout limits Timothy was originally trying to optimize.
Not the keys to the corporate bank account.
Definitely not.
But let's dig into the why here, because if you're listening to this and realizing you might have API keys sitting in your environment variables right now, don't panic. But Margaret is basically looking over your shoulder, shaking her head. Why is this so dangerous?
It really comes down to access vectors. Anyone on your engineering team with basic read access to the Lambda console can simply click a tab on their browser and see that key in plain text.
Just right there on the screen.
Right there. But the danger isn't just internal employees snooping around. Think about supply chain attacks.
Oh, no, those are terrifying.
They are. If a malicious actor manages to slip a compromised dependency into your code, maybe a rogue open source package you downloaded, that code can easily execute a command to dump the entire environment variable object.
And suddenly your payment key is sent to a server in another country.
Exactly.
But Timothy argued the data was encrypted at rest. Does that not protect against this?
Not at all. Encryption at rest simply means that the physical hard drives in Amazon's data centers are encrypted.
So if someone literally broke into an AWS server farm and stole a hard drive,
they couldn't read the data. But when an authorized user or compromised code running inside the Lambda function asks to see the environment variable, AWS transparently decrypts it and hands it over.
It does absolutely nothing to protect the key from application-level access.
None whatsoever.
That makes perfect sense. And Margaret brings up a secondary structural nightmare with this welcome mat approach, long-term maintenance.
A huge headache.
She points out that if the payment provider enforces a mandatory 90-day rotation policy, meaning you are required to change the API key every 3 months to stay compliant, Timothy's setup requires a human being to manually step in.
A developer would literally have to log into the console, manually update that environment variable with the new string of characters, and then trigger a complete redeployment of the Lambda function just to register the change.
Margaret calls that a security incident waiting to happen, and she is spot on. You are relying on a human developer to remember a deadline, to copy and paste a complex string without introducing a typo, and you are forcing a risky production code deployment just to update a password.
It's just bad practice all around.
If hiding the key under the mat is a terrible idea, we clearly need a better system. We need to build a real safe.
Which is exactly what Margaret proceeds to do. She introduces Timothy to AWS Secrets Manager.
A vault.
Yes. She describes it as a purpose-built, highly secure, encrypted digital vault. She takes the keyboard, navigates to the Secrets Manager console, and creates a brand new secret.
She gives it a very clear, logical path name, right? Something like Prod Payment Gateway Key.
Exactly. And she pastes Timothy's API key inside this vault.
One detail from the source I really appreciated is that she mentions they can define the secret inside their CloudFormation template, which references a lesson they had back in episode 55.
Right, maintaining infrastructure as code.
Yeah, they define the existence of the vault in their code, but they inject the actual sensitive value securely outside the code base.
What's fascinating here is how this vault actually locks its doors. The encryption algorithm is strong, certainly, but the true security mechanism is the deep integration with AWS Identity and Access Management.
Commonly known as IAM.
Right. Locking the vault isn't just about scrambling the data. It is about scoping permissions with absolute granular precision based on the principle of least privilege.
Explain how that principle applies here.
Margaret explains that access to this specific secret is strictly governed by IAM policy documents. When setting up the system, they don't just give the Lambda function a blanket permission to read all secrets in the account.
That would defeat the purpose.
Exactly. They scope the permission down to the exact secret ARN, the Amazon resource name, which is a unique identifier for that specific vault.
Wait, hold on. I need to push back on this for a second.
Yeah.
If Margaret is the senior engineer, and she literally wrote the Lambda function and set up the architecture, how can she not see the key?
It's a great question.
Doesn't she inherently have administrative access to the environment she built? That seems counterintuitive to how software permissions usually work.
It does seem counterintuitive at first glance, but that separation of duties is the core of zero-trust architecture. An IAM role is attached to the Lambda execution environment itself.
Okay.
That code has the explicit permission to call the getSecretValue action for that specific ARN. However, Margaret's personal IAM user profile, the account she uses to log into the AWS console, does not have that permission.
Oh, wow.
Yeah. She can edit the Lambda code, she can view the logs, she can manage the deployment pipeline, but the actual plaintext value of the key remains completely invisible to her. The code has the required security clearance. The human developer does not.
The code has the clearance, the human does not. There's a brilliant distinction. It completely removes the risk of an employee accidentally viewing and linking the credential.
Exactly.
But this raises a massive practical issue for me. If the vault is locked down so tightly and the key is no longer sitting in the environment variables ready to go, how does the application actually manage to get the key and process a customer checkout at runtime?
Because it still needs the key.
Right. The code has to send that API key over the network to the payment gateway to process the charge.
This is where we hit the crux of the architectural challenge in the narrative. This crucial question pivots our conversation away from pure security and directly into the friction that heavy security inherently causes at runtime.
Because security always comes with attacks.
It really does. We are entering the performance puzzle.
You can't just add a layer of encryption and API calls without paying a price.
And Margaret breaks down exactly what that penalty looks like. Calling the Secrets Manager API to fetch that key isn't free. From a billing perspective, it costs a fraction of a cent per API call.
Which adds up.
It does. But more importantly for Timothy's latency issue, it adds physical network latency. The Lambda function has to pause its execution, send a request over the internal AWS network to the Secrets Manager servers, wait for the IAM verification, wait for the decryption, and receive the payload back.
All of that takes time.
It takes several milliseconds.
A few milliseconds might not sound like a lot to a casual user, but at a massive scale, it is an absolute disaster. Margaret points out the math. If their e-commerce system processes 10,000 checkouts an hour, fetching that secret from the vault 10,000 separate times is entirely unacceptable.
Right. You are multiplying your network latency, slowing down the user experience, and racking up unnecessary AWS bill charges for repetitive API calls.
We have to solve how to unlock the vault during a real-time customer transaction without destroying the application's speed.
And the architectural fix Margaret implements to solve this is highly elegant. She teaches the code to unlock the vault at runtime, but she optimizes it by initializing a variable which she names cached secret outside the main Lambda handler function.
Yes, and Timothy immediately recognizes this pattern. He mentions it's exactly what they did to optimize a Redis database connection back in episode 64.
It's a very common, very powerful pattern.
But we need to explain why placing the variable outside the handler makes such a massive difference.
To understand the why, we really have to look at the mechanical reality of a serverless execution environment. When an HTTP request comes into AWS Lambda, there isn't a server just sitting there waiting.
Right.
AWS physically has to carve out CPU and memory on a host machine, download your code package, spin up a micro virtual machine or container, initialize the runtime, and load your code into memory.
And this entire initialization sequence is called a cold start.
Exactly. A cold start. And that cold start takes time.
It does. Now, any code you write inside the main handler function is executed every single time a request comes in. If you put your Secrets Manager API call inside the handler, it runs 10,000 times for 10,000 checkouts.
Which is what we want to avoid.
Right. But any code written outside the handler function only runs during that initial cold start.
And that is the secret sauce.
Here's where it gets really interesting, because this concept completely solves the latency problem. If we go back to our vault analogy, it's exactly like running a high-security bank.
Okay, I like a good analogy.
The bank teller doesn't walk all the way down to the basement vault, spin the giant heavy dial, and pull out a single $1 bill for every single withdrawal a customer makes.
That would take forever. The line would be out the door.
Exactly. Instead, the teller goes down to the vault once at the very beginning of their shift. They bring a batch of cash up to their local register, which represents our memory cache, and then they serve the next 100 customers instantly, right out of that local drawer.
That is precisely how in-memory caching operates in this serverless context. The very first checkout request experiences that cold start. The container spins up, the code initializes, it takes the cache miss, it reaches out over the network to secrets manager, takes the slate latency hit, and stores the retrieved API key in that global cached secret variable.
So that first customer waits a tiny bit longer.
Just a tiny bit. But crucially, after that first request finishes, AWS doesn't immediately destroy the container. It freezes it and keeps it warm in the background in case another request comes in soon.
The cache is in the register. The heavy lifting is already done.
Precisely. When the next 9,999 checkout requests hit that same warm container, they skip the initialization phase entirely. The code just reads the API key directly from the local memory variable.
You bypass the network latency entirely.
And you bypass the AWS API cost. You have successfully achieved lockdown, granular security without sacrificing the lightning-fast performance of the application.
It is basically the holy grail of software architecture. Fast and secure.
Hard to pull off, but amazing when you do.
But if there is one thing I know about engineering, it's that building the perfect system is only half the battle. Maintaining it is where the real nightmares happen.
Very true.
Okay, caching solves the speed issue perfectly. But I see a massive pothole ahead. If the code is caching the secret in local memory for hours at a time, what happens when that mandatory 90-day rotation hits?
Oh, right.
Doesn't the cache blindly hold on to the old expired key? How do we maintain this pristine system over time without creating an endless backlog of manual deployment work for our developers?
That is the exact trap we need to avoid, and it brings us to the final piece of the puzzle. Putting the entire security lifecycle on autopilot through automatic secret rotation, we cannot rely on humans to fix this.
Let's recall Timothy's original headache from the beginning of the narrative. If the external payment provider required a key rotation every 90 days, Timothy was going to have to manually update his environment variable and trigger a full production redeployment.
It is so tedious.
And worse, if he forgets, or if he's out sick on vacation when the 90-day limit hits, the whole payment system crashes because the external provider rejects the expired key.
Contrast that manual, error-prone nightmare with Margaret's final implementation. Because she made the architectural decision to isolate the secret inside AWS Secrets Manager, she unlocked a powerful native capability of the AWS ecosystem.
Which is?
The vault can be configured to automatically negotiate a new key with the payment provider on a set schedule.
We need to explain the mechanics of how that actually happens because it sounds like magic.
Right.
How does AWS know how to talk to a third-party payment gateway like Stripe or PayPal to negotiate a key?
It isn't magic, it is custom automation. Margaret sets up an entirely separate, isolated helper Lambda function.
Oh, a helper function.
Right. This helper function contains specific code written to interact with the payment provider's API. She configures Secrets Manager to trigger this helper function every 30 days.
So it just wakes up on its own.
Exactly. When it wakes up behind the scenes, it reaches out to the external provider, authenticates itself, and requests a brand new API key. It then updates the encrypted value stored inside the Secrets Manager vault, and finally, it runs a quick test transaction to verify the new key actually works before finalizing the rotation.
This completely eliminates manual human intervention.
Yeah.
Timothy never has to touch the application code. He never has to trigger a deployment. He doesn't even need to put a reminder on his calendar.
You can just focus on building the product.
Right. And addressing my earlier worry about the cache holding onto an expired key, because Lambda containers are naturally cycled out by AWS every few hours anyway, the cached secret variable naturally refreshes. The next time a container spins up from a cold start, it simply pulls the fresh, newly rotated key from the vault.
If we connect this to the bigger picture, this isn't just about saving developers from tedious, repetitive chores. The underlying philosophy here is about limiting what cybersecurity professionals call the blast radius.
The blast radius. Break down how that applies to our API key scenario.
When an explosive device goes off, the blast radius is the physical area of destruction. In cybersecurity, if a credential is ever compromised, say a developer accidentally logs it to a public dashboard, or a sophisticated attacker manages to scrape it from memory, the blast radius is defined by the amount of time and the level of access that bad actor has to inflict damage before the breach is closed.
I see.
Frequent automatic rotation is a critical best practice because it strictly limits that window of vulnerability.
Because if an attacker somehow manages to steal the API key on day 29, they might think they have the keys to the kingdom.
But they don't.
Right. That stolen key becomes completely useless to them on day 30, when the helper Lambda automatically negotiates a new one and discards the old one.
You are constantly pulling the rug out from under potential attackers.
Hmm.
And because the entire workflow is automated, you can safely rotate the keys far more frequently, every 30 days, every week, even every day, than you ever could if you relied on a human being to manually update the code.
So what does this all mean? Let's look at the ultimate transformation of Timothy's code from the beginning of the story to the end. He started out just trying to fix a minor latency spike, completely unaware that his most sensitive production key was essentially sitting out on the front porch for anyone to trip over.
A literal disaster waiting to happen.
By the time Margaret is done walking him through this architecture, his system isn't just fast. It isn't just resilient and observable. Its most sensitive data is protected from internal eyes. It is defended against external threats, and the entire security maintenance lifecycle is running entirely on autopilot.
It is a massive level up in engineering craftsmanship. It really is a masterclass in modern cloud architecture. Aaron Rose's narrative beautifully distills the complexities of serverless security into a highly pragmatic lesson.
Absolutely. So as we wrap up this deep dive, let's synthesize the core takeaways from the Victorian Library. We have seen that good architecture is fundamentally a balancing act. It is about leveraging purpose-built tools like migrating away from environment variables to AWS Secrets Manager and utilizing IAM policies to achieve lockdown, zero-trust security.
Furthermore, it is about deeply understanding the mechanics of your serverless environment so you can utilize patterns, specifically initializing variables outside the handler for in-memory caching to maintain lightning-fast application performance despite that heavy security layer.
And finally, it is about using automated rotation workflows to completely remove human error and drastically limit your blast radius. These are not just theoretical concepts for fictional developers. These are the exact pragmatic principles that protect your own production systems from catastrophic breaches.
This raises an important question, though, doesn't it, about where we go from here as the industry continues to evolve.
It does. And I want to leave you, the listener, with a final provocative thought to ponder on your own. We talked a lot about the difference between physical keys and digital keys at the beginning of this deep dive, and we just discussed the concept of limiting the blast radius by shrinking the window of vulnerability from 90 days down to a 30-day automated rotation. But let's take a hard look at the modern digital landscape we are operating in right now.
The speed of exploitation is moving faster every single day.
Precisely. We are living in a world where automated malicious bots can scrape an exposed credential from a public code repository and actively exploit it across thousands of endpoints in a matter of seconds, not days, not hours, seconds.
It's a scary thought.
So is even a 30-day automated rotation fast enough anymore? What would an architecture look like where credentials don't just rotate every month or every week, but are generated dynamically to exist for the exact microsecond a customer checkout occurs, and then vanish entirely from existence? As you go back to your own projects and lock down your own vaults, I'll leave you to think about what that ultimate zero-trust future might look like.